Hello, my name is Larry Lapides. I'm with Imperas Software, and today I'll be talking about RISC-V processor verification. My agenda for today is to provide an introduction to Imperas and then talk about RISC-V, why RISC-V is being adopted by so many companies. We'll go into the RISC-V processor design verification issues, talk about the 5 levels of RISC-V DV methodology, and then 2 key pieces of technology, the reference models and the verification IP, and then we'll summarize. So let's start with an introduction to Imperas. The Imperas founding team has a background in design automation, EDA tools, as well as with FPGA and processor IP companies. We saw the need to provide tools and methodologies similar to EDA for software debug, test, and analysis based on software simulation. Just as no SoC is developed without significant simulation and with verification tools on top of simulation, we believe the embedded community is evolving so that no embedded system will be shipped without significant simulation-based verification of software. A key Imperas differentiation is that our products have been architected from the tool requirements down, not the modeling requirements up, and this provides significant flexibility and performance advantages. Recently, with the introduction and adoption of RISC-V, Imperas has added DV technology and methodology to our portfolio. So a bit of history with Imperas and RISC-V. We first encountered RISC-V at the Design Automation Conference in 2016, so about 5.5 years ago now. And RISC-V looked like an academic project. It looked fragmented. And 6 months later, at the RISC-V workshop in Silicon Valley at Google, with 350 attendees, the ISA, the instruction set architecture, looks to be converging. And so we joined the RISC-V Foundation. We built our first RISC-V processor model, and we started participating in the RISC-V community, specifically in the compliance working group. And we built and donated an instruction set simulator and compliance tests. Our next step was to introduce a methodology for adding and optimizing custom instructions for RISC-V cores. We had our first paying customer in 2018 for RISC-V models for both software development and design verification. And then in 2019, that first paying customer taped out their first SoC based on using the Imperas reference model as the DV reference model. We started collaborating with Google on DV flows with the Google open source instruction stream generator. So we've moved from just compliance to full DV. We're working with the Open Hardware Group and individual members of the Open Hardware Group on DV of the Core 5 cores. And then about a year ago at DVCon in Silicon Valley, we presented 2 papers on RISC-V processor DV, one in collaboration with Open Hardware and the other work with NVIDIA Networking, the Mellanox group here in Israel. And then at the RISC-V Summit in December of last year, we introduced our Imperas DV RISC-V verification product line. So we've been an active member of the RISC-V community. I would say the leading member of the RISC-V ecosystem for the last 5 years. There's a nice list of users and partners that we work with. I think the key thing here is that the most complex RISC-V processor projects use Imperas, with 3 known exceptions right now. But if it's RISC-V and there's any complexity, people are using Imperas. So why RISC-V? Why has RISC-V become so popular? Why does it have so much momentum in the industry right now? So RISC-V is an open standard instruction set architecture, began in 2010 at the University of California, Berkeley. Unlike most other ISAs, RISC-V is provided under open source licenses that do not require fees to use, but this is just the architecture, not the processor implementation. Unlike other academic designs, which are typically optimized only for simplicity, the designers of RISC-V intended that this instruction set be usable for practical purposes. And while the ISA is a comprehensive RISC architecture, the RISC-V specification allows for users to add custom features, instructions, CSRs. It's this freedom and not the free, which is why RISC-V usage is growing so fast. This freedom, the ability to customize the RISC-V processor, enables domain-specific processing. So RISC-V is growing in market segments where x86 and ARM are not dominant, in small microcontrollers for SoC management, often replacing proprietary cores, in verticals such as IoT and AI, and also in horizontal markets such as security, which cuts across all these different vertical segments. The freedom of the Open ISA enables users to develop differentiated domain-specific processors. That gives companies an advantage. So the RISC-V users include traditional semiconductor companies and also embedded systems companies now practicing vertical integration by developing their own SoCs. So what are the processor design verification issues for RISC-V? Every feature selection, every choice that is made requires serious consideration due to the implications of these choices. The experienced processor teams know the costs associated with every feature. Every addition dramatically compounds the verification complexity. The costs of a simple added feature can be huge, and this can be unknown to inexperienced teams. There are schedule, resource, and quality implications. These imply risks. As of 2021, there's no off-the-shelf toolkit for DV of RISC-V processors or any processor. No EDA vendor has a RISC-V DV kit. There are in-house processor DV solutions at Intel, at AMD, at ARM, but these are not generally available. And so again, building your own processor is going to add schedule, it's going to require resources, and you have quality considerations as well. These are risks. And the risks are manifested as costs. SoC costs is about 50% for hardware DV, assuming the CPU is bought in as proven IP. So developing your own CPU adds a huge incremental cost. And you better get it right. There are 5 levels of RISC-V DV methodology, starting with Hello World, just basic bring up of your processor, the self-checking tests, such as the Berkeley torture tests, post-simulation trace log file compare, synchronous step and compare, and asynchronous step and compare. I'm not going to go into detail on all of these, but let me just touch on 2. So let's start with the post-simulation trace log file compare. We would call this entry-level DV. In this methodology, a random generator, an instruction stream generator, is used to create tests. During simulation of the reference model, the ISS, a trace log file is written. During simulation of the RTL, a trace log file is written, and then both log files are run through a comparator to see the differences and the failures. The key pieces of this are the reference model, the ISS. RISC-V OVP Sim Plus is commonly used for this. It's available on the Open Virtual Platforms ovpworld.org website. And for the instruction stream generator, RISC-V DV from Google is typically used, available from their GitHub repo. The fifth level of DB methodology is asynchronous step and compare. This is the highest quality DB methodology. Design features needing this methodology include out-of-order and multi-issue pipeline, multi-heart processor, debug mode, interrupts, and more. And so to build this sort of methodology, you need some components in your SystemVerilog or in your test bench. You need a tracer, you need step and compare, you need interrupt assertions, debug assertions. In this slide on the right here, that comes from Open Hardware, this test bench is built in SystemVerilog. This is a UVM test bench, or getting close to full UVM compliance. And the Imperas reference model is wrapped in a SystemVerilog DPI wrapper. The thing with this is that it's typically difficult, complex, and expensive to get working. And one of the key challenges is extracting the asynchronous information from the RTL pipeline. So let's summarize what we're doing here with asynchronous step and compare. There's instruction by instruction lockstep comparison. It's an immediate comparison. It allows for debug introspection at the point of failure. That's very powerful. But it also, because it's doing that introspection at the point of failure, it does not waste execution cycles after failure. So it's focused on the asynchronous events. It supports multi-heart processors and out-of-order multi-issue pipelines. It can be hard to develop and set up. It can be expensive in terms of time, resource, and licenses. So it can cost a lot per bug found, but bugs are even more expensive if not found early enough. So this is the most comprehensive and most efficient DB approach, but there are some improvements that can be made. The next steps for this asynchronous step and compare methodology are standards for the test bench and verification IP. So let's go talk about these things. Let's talk about reference models, the verification IP, and the standards. The RISC-V processor DB environment has 5 major components: the functional coverage, the tests, which can be either instruction stream generator or directed tests, the DUT subsystem, the test bench itself, and the reference model subsystem. There's a new RISC-V DB standard called RBVI for interfacing to the test bench. And the key DB technologies here are the verification IP, these DB functions, and the reference model. That RBVI standard is available on this GitHub repo. This is a public standard, and it helps both with the interfacing of the DUT subsystem as well as the reference model subsystem to the test bench. I won't go into any more detail on that. You can go to the GitHub repo for more information. And just one more word here about the DUT subsystem. A key piece of technology is the tracer. The quality of the tracer in the RTL determines the potential capabilities of the DB environment. This is the component that provides the introspection into the RTL. So let's go to the 2 key pieces of methodology or of technology, the model and then the verification IP. So starting with the RISC-V model, this is not just for DB, it's also going to be used for software development. What you want is for the software team to be developing on the same technology, the same code base that the RTL guys are on. That ensures synchronization between your 2 groups. So what do you need to do? You need to model the ISA, including all versions of the ratified spec and the stable unratified extensions. You need to easily update and configure the model for the next project. Needs to be user extendable. Need to be able to model actual processor IP. Need to have a well-defined test process for the model itself, including coverage metrics. Need to have interface to other simulators, interface to software debug tools, interface to software analysis tools, interface to architecture exploration tools. Most RISC-V instruction set simulators can meet one or two of these requirements. We've been building our models and simulators for over 12 years, working on not just RISC-V, but other instruction set architectures, and we satisfy all these requirements. So just looking in a bit more detail at the Open Virtual Platforms library of RISC-V fast processor models. We're supporting generic or envelope models, models of the processor IP vendors, models that users build, and custom models can be supported here. A key piece of this is the test-driven development methodology that is used for building the models. The tests are built at the same time features are added. We use a continuous integration flow. There are over 15,000 tests for the models in the simulator, and there is additional testing by the processor IP vendors to validate the models. Just to provide a bit more detail here, this is the architecture of the reference model, which actually has the reference model itself built with a set of APIs and the Imperas simulator engine. And then there's the ability to configure the model to support the extensions that you're using, the versions of the extensions, various other implementation-specific details. Over 150 different parameters are available to configure the reference model. And these reference models are open source, provided under the Apache 2.0 open source license. To add custom instructions and CSRs, there's an extension library that's used. And again, this is the same APIs as in the base model. It's supported by the simulator. All the tools work with the custom instructions. So the advantage here is that the base model doesn't get touched. The base model is used actually by all the different Imperas users. And so it gets tested not just internally by Imperas, but this base model gets used by everyone, tested by everyone. It is as solid a piece of code as there is. So let's go into a bit more detail on adding custom instructions. What does it take to add custom instructions to the reference model? In the RISC-V world, adding custom instructions is done to optimize a specific application or set of applications, a domain. And so you're going to want to characterize the C application. You can do this with simulation of this application. So here again, you're using the reference model not just for DD, but you're also using it to run software. This is instruction accurate simulation, so it's going to run very fast. However, even though it's instruction accurate and doesn't have detailed cycle information, there is a lot of information that you can extract. So for example, you can do function profiling of the C application. And here we see that the process line function in this application is 21% of the overall execution time. So what we're actually doing here, this is a real example where we're adding cha-cha-20 encryption instructions to the RISC-V processor. So now we're going to develop these new custom instructions. We're going to add these custom instructions into the application. When we simulate, we get an unimplemented instruction exception in the simulation because we haven't added the instructions to the model. So now we go and do that. In this new extension library, we add these instructions in. We add this to the decode table. Works quite well. And now actually we see that the instruction count and the simulated time have been reduced. As I mentioned, the Imperas architecture allows these custom instructions to use all the tools that are available in the environment. And so we see tracing is going to work. We see the cha-cha-20 instructions here in the trace. Debug is going to work. You can see the instructions in the debug window in your debugger environment. And profiling works. And we see actually that process line function has been reduced from 21% to 16% of the overall execution time. In this custom instruction flow, you're now going to iterate that until you're happy with it. You're going to optimize and document the model, and then release and deploy. So this is the reference model that you're going to be using, not just for DV, but for software development. It needs to support the complete RISC-V specification, but it also needs to be able to handle custom instructions. So this is one key piece of technology. The second key piece of technology is the verification IP, the Imperas DV piece of this. Verification IP is needed for ease of use. It's needed for scalability, because this is not the only RISC-V core you're going to use. Extendability, you're going to want to add those custom instructions and be able to verify those in the environment. It's needed for improving performance of your DV environment, for debug, and for schedule reduction. So that block of DV functions looks like this. In practice, you're able to select the model, use the variant, configure a specific variant. It provides the encapsulation, including instruction coverage on the reference model. It includes DUT reference state storage, synchronization technology, comparison technology. And this can be used not only in SystemVerilog test benches, but also in C, C++ test benches, and it uses the RVBI API. Seeing this as part of the DV environment, we don't have the test, we don't have the functional coverage shown here, but here we have the device under test, we have the test bench, we have Imperas DV. Again, we're doing the setup, we're configuring the registers in memory, we're selecting what to compare. Again, this depends on the DUT tracer capabilities. We're selecting the comparison capabilities. We're doing the trace and logging setup. We're selecting the instruction coverage. And again, we've got the encapsulated reference model in here. And this is all communicating with the test bench using the RVBI APIs, and then the Verilog device under test, or SystemVerilog device under test, is also communicating with the test bench here. So by having this, we're making it easier to do DV. We're accelerating our schedule. We're providing a more comprehensive environment. In summary, RISC-V processor developers need to do comprehensive verification of the RTL implementation. Processor DV methodology has been evolved by Imperas together with our customers and partners. The asynchronous step-and-compare methodology provides the most comprehensive, most efficient RISC-V DV flow. The key technologies include the Imperas OVP reference model and the Imperas DV verification IP. Thank you very much for your time and attention. please feel free to contact me with any questions.